Here we're looking at the 2011 test for Unit 5, Question 1. The graph shows the variation with applied potential difference V and current I in electrical component. Which of the following gives the resistance of the component at point P? Now, the definition for resistance is given by this, and it's the ratio of the voltage to the current at that specific point at that specific time. So it would be this one over here, that it would be V1 over I1. So D would be correct. The whole thing about the gradient or the reciprocal of the gradient just comes in with Ohm's law. In Ohm's law, your gradient equals the resistance because it's a constant gradient. For Ohm's law, we have a graph like that where you have got a proportional graph, V against I. So in that case, your slope or the gradient does equal to the resistance. But in other components where that isn't the case, whenever you want to find a resistance at a certain point, it's just those values, V1, I1, V1 over I1 is equal to the resistance. Question 2. Now, when doing these, I always like to put in a number. It just helps me think of things. So we have the diagram below shows the combination X, Y, and Z of 3 resistors, each resistor having the same resistance. So I'm going to say, okay, each of these is 2 ohms. You can just pick a number. 2 always works well for me. So, and then just work out the resistance for each. Now here we've got a parallel section. So the resistance of that is going to be 1 over R parallel is equal to 1 over 2 plus 1 over 2, which is equal to 1. So this part over here, Rp, which is the inverse of that, 1 over 1, which is equal to 1. So this will have a combined resistance of 3 ohms, the 2 ohms plus the 1 ohm there. For this one over here, we've got in parallel, these two are in series, so that's a combination of 4. So 1 over Rp would equal 1 over 2 plus 1 over 4, which is over 4. So it's going to be 2 plus 3 over 4. So we're going to get 3 over 4 is equal to 1 over Rp. Your R for the parallel section will be 4 over 3, which is equal to 1.33 recurring ohms. So here we are having that this is about 1.33 ohms. And then for this one over here, to work out the total for that parallel section is 1 over 2 plus 1 over 2 plus 1 over 2, which is equal to 3 over 2, which is equal to 1 over R. Then we invert both sides, so R is equal to 2 over 3, which is equal to 0.66 recurring 7 ohms. So this is 0.667 ohms. So now it's pretty easy. We know that this one is the smallest, this is the next smallest, and this is the next, that's the biggest. So we're going from lowest to highest, so it's going to be Z, Y, X. It's going to be D. Okay, so by putting in numbers, it makes it that much easier. Going on to this one over here, we have a battery of EMF E and negligible internal resistance is connected to 3 resistors, each of resistance R, so they've got the same resistance, a voltmeter and a switch, as shown below. Now just this first part over here, when it says it's got an EMF E of negligible internal resistance, now that means that there's no energy loss within the cell. So the potential energy, electrical potential energy loss within the circuit must equal to that E. So if I've got a voltmeter there, let's call that V1, and another voltmeter there, V2, that would add up to your voltmeter reading across your cell, which is equal to E. So V1 plus V2 is going to be E. So let's have a look at this. What are the readings on the voltmeter when the switch is open and when it is closed? Alright, so let's have a look at when it's open firstly. Now when it's open, that means that we've just got 2 resistors that are in series with one another, and because I got the same resistance and we had the same current going through both, V is equal to I times R. Therefore, V1 must equal V1 equals V2. So when switches open, each of them are going to be half E. All right, it's going to be half E, so it's going to be this one or this one. Okay, now so we've got that. All right, now let's close the switch now. When we close the switch here, now the current is actually going to be able to go there and there in two different paths. So actually what's going to happen is that the resistance is actually going to be decreased. So let's just think about that. The resistance is going to be decreased. So the combined resistance for this parallel section here, the combined resistance for that 1 over Rp will equal 1 over R plus 1 over R, which is going to equal 2 over R, which is 1 over Rp. Therefore, Rp for that will equal R over 2. So we've actually could replace these two by one resistor, and it's going to have a resistance of R over 2, or half the resistance, which makes sense because we have got two paths each going through resistance, so we've doubled the amount of conductor or area which the charge can go through. So now what's going to happen? Well, because V is equal to I times R, the I will still be the same, will still be going through both, although it will actually increase, but it will still go through that one, come back and go through that one over there. So this V here is going to be less than this V over here, because this has got R and this got R over 2. So you're actually going to get an increase here for your you're going to get an increase there for your V there, and you're going to get a decrease here. So it's going to be less than a half E there, so it's going to be C. If you have any questions on that, maybe I didn't explain that so well. Let me just say it again. Because in parallel, let me just say this all again. This resistance, the resistance goes down. Therefore, V is equal to I times R. That resistance will go down. Therefore, your V is going to go down. And therefore, this V is going to actually decrease. For question 4, it says a proton and an alpha particle are accelerated from rest through a positively charged plate X to a negatively charged plate Y. Okay. At the midpoint between the plates, the proton has a kinetic energy of Ek. At this point, the alpha particle has a kinetic energy of what? Now, we're actually using this formula over here, that our VE is equal to a half mv squared. So the potential difference, this V, so let's have a look. We've got our proton and we've got our alpha particle, which remember is 2 plus. This is going to be VE, is going to give our kinetic energy. And here, because the alpha particle has got a 2 positive, this is going to be 2 VE. So at the midpoint, the proton has a kinetic energy of Ek. At this point, the alpha particle is going to have double that. So your answer there for question 4 would be C. Question 5. We have the graph below shows the variation with voltage V of the current I in 3 resistors X, Y, and Z. Which of the following corresponds to resistors for which the resistance increases with increasing current? Now, we've got it I against V. I usually like to do it as V against I. And if I did that, these graphs would look like this. You would have Y, which is like a proportion graph. We would have the Z, would be a graph like that. and we would have the X would be a graph like that. It would be inverted around. So because our resistance is equal to V over I, we can see here that the ratio of V as to I is actually increasing in X here, because V as to I is actually going to increase. If I took this amount over there and I did my V against I, let's say this was 1 and this was 1, it would be, you would get a resistance of 1. If I went over there, say that is 2, 3, and I went over there, I think you can see that this amount here has increased more than just 3 times. And so your resistance there, R is equal to V over I, would have actually increased. And so you're getting an increasing resistance for X. So A would be correct there. For question 6, it says the element of an electric heater has a resistance R when in operation. What is the resistance of a second heater that has a power output 3 times as large as this at the same operating voltage? Now here obviously we're using these formulas over here, and because we're dealing with potential difference and resistance, we would have our power is equal to V squared over R. So we have a power output here of 3 times the power. Our V squared is staying the same because we have the same operating voltage. So therefore, what must our R be? Well, we must decrease that by 3. Must be a third of the amount, so the answer would be B to give you your 3P, like that. Here we have something quite similar sort of question. It says in 2 circuits X and Y below, each cell has an EMF of E and negligible internal resistance. So remember that if you put a voltmeter across there, you would get a potential difference there of E, and here the same thing, you'll get a potential difference here of E, same amount, because of the negligible internal resistance. All the energy would be lost in the circuit itself. The power dissipated in circuit X is P. The best estimate for the power dissipated in circuit Y is, well, what is the resistance of this? Well, because they are in parallel, 1 over R parallel, which is equal to 1 over R plus 1 over R, which is equal to 2 over R, which is 1 over RP. When I invert that, I get RP is equal to R over 2. So my power, using this formula again here, my power in the first one is E squared over R. And my power in the second one is E squared over R, R over 2. Now when I divide by a fraction, I invert in times, so that equals 2E squared over R. So I actually get obviously twice the power. So I'm going to get that over there. And finally going on to our last question over here. This is just a bit of knowledge. The drift velocity of electrons in copper wire in which there is an electric current, it's of the order of a few millimeters per second. I mean, these are tremendously high speeds. Remember the electron which is going through there are millions of these electrons. There's a large quantity of those electrons, but they are interacting with the electrons within the metal itself. So they are hitting these, bouncing off them, and so their path is very jagged through the material as they interact with those electrons within the copper wire.